Tonight, I am taking you on a journey across the impossible. We are going to drift across our entire galaxy and calculate exactly how long it takes to cross the void. Here is what most people do not realize from down on Earth. The Milky Way is so staggeringly vast that even at speeds I find terrifying. Crossing it takes longer than you can imagine. By the end of our voyage, you will understand just how isolated I feel out here in this massive cosmic structure we call home. Before we drift further, if you love exploring the deep space abyss like I do, take a second to like and subscribe. It is a simple click, but it helps me reach more curious minds. Now, let us look out the viewport and start with the fundamental question. How long does it take to cross the Milky Way from one edge to the other? Looking out from my station, it is about 100,000 light-years across. A light-year is the distance light travels in 1 year. It moves at 186,000 miles per second, or 300,000 kilometers per second. In a single year, light covers 5.88 trillion miles, or roughly 9.46 trillion kilometers. So, when I say the Milky Way is 100,000 light-years across, it means 588 quintillion miles, edge to edge. That is 946 quintillion kilometers. That is the distance I am staring into. Understand, this conventional rocket speeds are utterly inadequate for this journey. The fastest human-made object is currently the Parker Solar Probe, a NASA ship I have watched closely. It reached 430,000 miles per hour, or 692,000 kilometers per hour. That is incredibly fast. Roughly 1/1500th the speed of light. Fast enough for me to circle Earth in less than 6 minutes. It is the fastest thing we have ever built. Yet, at that speed, crossing our galaxy would take me over 150 million years. That is a massive chunk of time. Chemical rockets, ion drives, nuclear propulsion, none of my gear can handle this. These systems are all too slow. Galactic distances dwarf anything my spacecraft can achieve. I have to think in terms of light speed. Light is the fastest thing out here. Nothing with mass can reach it. But for our journey, let us imagine I could. At exactly the speed of light, crossing the Milky Way takes 100,000 years. That is 100 millennia in the dark. That is the span from when humans first left Africa to the moment I am speaking to you now. If I left one edge at light speed when modern humans first walked the Earth, I would only be reaching the far side at this very moment. Even the fastest thing in existence needs 100 millennia. But out here, relativity changes the entire game. According to Einstein, time slows down as I approach the speed of light. From my seat in a ship moving that fast, the journey would feel instantaneous. No time would pass for me at all, but for someone watching my ship from the outside, the trip still takes 100,000 years. This is the eerie nature of relativity. Time is not absolute. It depends on how fast I am moving. Of course, no object with mass can actually reach light speed. The closer I get, the more energy I need. It would take infinite power to reach it. Let us be more realistic. At 99% the speed of light, the journey takes 101,000 years from an outside view, but time dilation kicks in. For me, the traveler, only 14,000 years pass. That is still longer than all of human history. Pushed to 99.9% light speed, I would experience 4,500 years while 100 millennia pass outside. At 99.99%, my ship clock would only record 1,400 years. If I hit 99.9999999% light speed, that is 7 nines, the time dilation becomes incredibly extreme. The journey takes 100,000 years from the outside, but only 1.4 years for me. That is less than 17 months in space. Suddenly, crossing our galaxy does not sound so impossible. From my perspective, it is a long trip, but fits within a human lifetime. This is comparable to a long ocean voyage in the age of exploration. Near light speed travel and time dilation make my galactic crossing theoretically survivable. It is not easy, or close to my current tech, but possible in principle. Of course, the practical problems are enormous. First, I have no way to accelerate this ship to 99.99999% light speed. The energy requirements are staggering. To push my small spacecraft to that speed would require more energy than humanity has produced in its entire history. Second, even if I could reach that speed, traveling through interstellar space at those velocities would be incredibly dangerous for me. Space is not empty. Hydrogen atoms, dust, and rocks are floating everywhere. At my normal speeds, they pose no real threat. But at 99.999999999% light speed, a single hydrogen atom hits me with enormous energy. A tiny dust grain would impact like a nuclear bomb. I would need shielding so advanced it is beyond our current understanding of material science. Third, even if I survived, a serious problem waits at the end. 100,000 years would have passed back on Earth. Everyone I knew would be gone. Civilizations would have risen and fallen. Humanity itself might have changed beyond recognition or simply ceased to exist. I would be traveling into the far future with no way back. These are not small obstacles. They are fundamental challenges. But the point is not to plan my actual journey across the Milky Way. It is to understand the scale involved and what physics tells us about the possibility. At everyday human speeds, crossing the Milky Way is essentially impossible. The time required is longer than the universe has even existed. Even at light speed, it takes 100,000 years from the outside, but time dilation makes it survivable for me if I can get close enough to light speed. From my cockpit, the Milky Way looks impossibly vast, but there is one thing we have not talked about yet: the route. You might assume we would just fly in a straight line. But what if we chose a more dangerous path? What if we flew right through the galactic center? We sit roughly 26,000 light-years from the galactic core. From here, we are about halfway between the center and the outer edge. If I steered us straight through that core to the opposite side, the journey would cover a staggering 100,000 light-years. But aiming for the center is suicide. Out here, stars are sparse, but in there, everything is crowded together. Near the very center lies Sagittarius A star, a supermassive black hole 4 million times heavier than our Sun. From my perspective out here, getting too close to that void is pure suicide. Its gravity would shred my ship. Plus, the radiation levels near the core are absolutely lethal. We are talking X-rays and gamma rays blasting from the accretion disk and other violent energy sources. We would need massive shielding just to survive. So, maybe we go around instead? After all, the Milky Way is a spiral. The galaxy is a disk with spiral arms reaching out from the center. If I follow those arms, the path is longer, but I can stay away from the most dangerous regions. Taking the long way costs us more time, but it significantly increases our chances of actually making it through. Space is not uniform. The spiral arms are thick with stars, gas, and dust, much more crowded than the gaps in between. I have to chart a course through the quieter, emptier spaces to make sure we do not collide with any interstellar debris. Even with the perfect route, avoiding the crowded center and the dense star nurseries, we are still crossing 100,000 light-years. From the outside, the journey takes 100,000 years, but for us to survive, we have to push our ship extremely close to light speed. There is no escaping the hard limits of physics, the vast size of the galaxy, and the speed of light. You and I have to wonder, what would we actually see through the viewport along the way? Imagine you and I are in a ship pushing 99.9999% the speed of light. The crossing takes only 17 months of ship time. What would we actually see? First, reality warps around us. The stars ahead would turn blue, their light compressed into intense, high-energy waves. Looking back, the stars would fade to red as their light waves stretch into lower energy. Forward is bright and blue, behind us is dim and red. Then, we hit an effect called relativistic beaming. Light that usually scatters everywhere gets crushed into a single blinding beam pointed directly where we are headed. Nearly all the light I see comes from the front. It is like staring down a narrow, glowing tunnel. My peripheral vision is squeezed into a cone ahead of me. Stars do not twinkle, they streak past my window every few seconds. To an observer, we take years to cross between stars. To me, the entire structure of the galaxy is just unfolding. I watch the spiral arms and the dense regions packed with young blue stars pass by. Eventually, the quiet gaps and the thick halo of ancient stars surrounding the galaxy appear. Then, I would watch the galactic center approach a blinding glow of millions of stars packed impossibly tight. I would feel the hum of radiation from Sagittarius A star from a safe distance if my navigation holds. As we pass the core and head for the far edge, I see the whole structure again from a new perspective. The spiral arms flip, and the disk's edge slowly approaches. It is the most beautiful voyage a human could take. But the loneliness? It is unlike anything you have ever felt. My 17 months of flight means 100,000 years pass on Earth. Everyone I ever loved is dust. That is the cruel paradox of near light speed. It keeps me alive for the journey, but it cuts me off from home forever. Now, we have to talk about the energy. The energy needed to push us to these speeds is terrifying. Pushing just a 1-ton ship to 99.99999% requires 90 quintillion joules of energy. That is 90 billion joules just to get moving. To put that into perspective, the total energy consumption for all of humanity in 1 year is 600 quintillion joules. Accelerating a single 1-ton ship would eat 15% of that annual supply. And that is just the movement. It does not even count the massive energy lost through engine inefficiencies. A real mission would need triple that energy. Besides, a 1-ton spacecraft is basically just a tin can out here. My ship needs life support, shielding, and supplies for a journey lasting months. A real vessel carrying humans would mass far more than just a single ton. The space station weighs 420 tons. Our deep space vessel would have to be at least that big. If we scale up to a 420-ton spacecraft, the energy we need scales too. We would require 60 sextillion joules. That is 100 times more energy than all of humanity uses in a year. Chemical rockets? Not a chance. The fuel itself would weigh more than the ship, and you need fuel to move that fuel. It is a vicious cycle. Nuclear fission or fusion might work in theory. Antimatter is our best hope. It is the most energy-dense process known, turning raw mass directly into power. Based on Einstein's equation, E=mc², if I annihilate 1 kilogram of matter with antimatter, I get 180 quadrillion joules of pure force. To move our 420-ton ship to near-light speed, I would need to annihilate 3,300 kilograms of matter with an equal amount of antimatter. We are talking about 6.6 tons of matter and antimatter fuel. It sounds massive, but it is conceivable. My concern is we cannot store antimatter in those amounts. Total human antimatter production is currently measured in nanograms, mere billionths of a single gram. I would need trillions of times more. Plus, I must store it safely, since contact with matter causes instant annihilation. These engineering hurdles might actually be insurmountable. But let us imagine a future where we finally solve this. We learn how to harness it all. We build a ship with high-tech shielding and life support. Then, we launch at 99.99999% light speed. I experience 17 months of travel as the whole galaxy unfolds before me. We cross 100,000 light years to reach the edge. But back on Earth, 100,000 years passed. The world I left is long gone. Any signal I send home takes another 100,000 years to arrive. I am totally alone. This is the grim reality of space travel. Even near light speed, the isolation is total. You and I can cross the galaxy in a single lifetime from our perspective. But I can never go home. Now, let us imagine we wanted to explore the stars instead of just crossing them. We could stop at star systems and hunt for alien life. That choice changes everything. Now, we are lingering. Imagine I want to visit 1,000 different star systems. We would sample the whole structure from the glowing center out to the dark, distant halo. Average jumps are 5 light years, but in the galactic core, the stars are packed much tighter. They are only 1/10 of a light year apart there, but 20 light years out in the halo. Averaging 5 light years per jump, visiting 1,000 systems means a 5,000 light year journey. At that speed, 5 millennia pass outside. But for me, inside the ship, it is only 10 weeks. 10 weeks sounds easy, but then I have to add time for exploration at every single stop. That totals roughly 19 years. My total mission time comes out to about 19.2 years in this cabin. That fits within my lifetime, but here is the terrifying reality. Outside, time moves differently. Travel takes 5,000 years, plus those 19 spent exploring. 5 millennia pass back home while I age 19 years. We leave in 2025. I return in 7044. Every culture and language I knew has simply vanished. This is the tragedy of exploring our galaxy. Time dilation saves me, but kills my connections at home. Could we just go slower? If we crawled at 10% light speed, you and I would age at the same rate. But then travel time hits 50,000 years. I would never survive. That is longer than all of recorded human history. We would need a generation ship where families die in the void. I would be dust before arrival. My descendants would see the stars. This is the brutal trade-off we face out here. Going slow keeps us connected, but the trip outlasts our entire civilization. There is no easy fix. Space is just too big. But consider this. What if we sent a signal, just pure data beamed across the stars? How long would that take? Even light has its limits. A beam of light takes 100,000 years to cross the galactic disk. The reply takes 100,000 years. That is 200 millennia. That is twice as long as we have even existed as a species. Even if someone is out there, you and I know this time lag makes conversation impossible. I could send a message, but we would be extinct before the answer. This is why we search for signals instead of a two-way conversation. When I stare into the void, I know any signal we catch is just a message in a bottle, sent millennia ago. It's no conversation. It's stellar archaeology. Out here, we're studying ghosts from the distant past, with no way to tell if their world even exists anymore. If I sent a reply right now, it wouldn't arrive for thousands of years. In this galaxy, real-time talk is a dream. The scale just won't allow it. Even a simple shout into the dark is a struggle. This crushing isolation is literally woven into the fabric of our universe. Light has a speed limit. The gaps between stars are massive. Together, they build a wall I can't climb. I can see the far reaches of the Milky Way, but only as they were, never as they are. No one will ever hear my reply. That's the cold reality of a home 100,000 light-years wide. Let's you and I look at this together from another angle. Instead of how long a crossing takes, consider how much ground I could cover. Imagine my ship is pushing 50% the speed of light. That's fast, but not enough to warp time completely. At half light speed, time only drags by a factor of about 1.15. My life on board would feel mostly normal compared to Earth. Let's say I have one 80-year lifetime to explore. How much could I actually see? At half the speed of light, I'd only cover 40 light-years before my time ran out. 40 light-years is a speck. It's just 0.04% of the way across this massive spiral we call home. If I spent my entire life drifting at half light speed, I wouldn't even cross 1/20th of 1% of the galaxy. To cross the whole thing, it would take 2,500 of my lifetimes. That's 200,000 years of travel. Modern humans have only been around for about 300,000 years. A single crossing would swallow almost our entire history. What if we dedicated every second of human civilization to this one journey? Our written records go back 5,000 years. At half light speed, I'd only make it 2,500 light-years out. That's a mere 2.5% of the distance. I'd need 40 of those 5,000-year trips just to reach the other side. 200,000 years. No matter how I crunch the numbers, the math always leads me back to the same grim truth. Crossing the Milky Way takes many millennia, unless I move at nearly light speed and let time dilation warp my very existence. There are no shortcuts out here. The galaxy is too big, and light is too slow. Galactic travel is an impossible mountain to climb. Could there be a loophole? Maybe you and I can find one in wormholes, warp drives, or some other science fiction trick. These ideas come from Einstein. He taught us that gravity is just the way space-time curves and bends. Massive stars and black holes warp the space around them, and everything else just follows those invisible curves. If I could fold space itself, I might find a shortcut. A wormhole would be a secret tunnel connecting two points in the dark. If a tunnel linked one edge of the galaxy to the other, I could step through and be there instantly. No long years of waiting. The catch is, I don't know how to build one. Physics says I'd need exotic matter with negative mass just to keep the door open. I've never seen anything with negative mass. It might not even exist, let alone be something I could use to navigate. For now, wormholes are just ghosts. Warp drives are the same. The idea is to move space itself, not move through it. I'd shrink the space in front of my hull and stretch it out behind me, riding a bubble faster than light itself. It doesn't break the rules because I'm not racing through space. I'm literally dragging the universe along with me. But again, I need that exotic matter. The energy required to blow that bubble might be more than the entire visible universe can provide. Even the best theories still require negative energy and power levels I can't even begin to comprehend. There is no way to build this. Warp drives are beautiful in movies, but they aren't a real way for me to cross the stars. Not with what I know today. Maybe a future breakthrough will change my reality. Maybe there's a secret to space-time I haven't found yet. But looking out this window, light is the limit. And at that speed, it takes 100,000 years to reach the far side. Let's zoom out even further. Crossing my own galaxy is one thing, but what about the local group? That's the cluster of 50 galaxies we belong to. It stretches across a staggering 10 million light-years of empty space. At light speed, the trip takes 10 million years. That's longer than my entire human lineage has even been walking. My species, Homo sapiens, is only 300,000 years old. Even my entire genus only goes back 2.5 million years. My whole evolutionary line, since we split from the apes, is only about 6 or 7 million years deep. Crossing this group takes longer than we've existed. But stay with me, the Virgo supercluster is on a whole different level. It holds the local group and countless others. It's a span of 110 million light-years. At light speed, the journey takes 110 million years. The dinosaurs died out 66 million years ago. Before that, they ruled the Earth for about 170 million years. If I tried to cross the Virgo supercluster, it would take as long as the age of the dinosaurs. But crossing the whole observable universe? From my view, the observable universe is 93 billion light-years wide. But it is not just a matter of waiting 93 billion years. Even at light speed, the trip stretches because the universe is expanding. While I am out here traveling, space itself is pulling apart. My destination is literally running away from me. If the expansion is fast enough, I might never reach that far edge. At light speed, space might still pull away faster than I can fly. This is the absolute wall I am hitting. It is not just about light. The expansion itself is the problem. Parts of the deep void are fleeing from me faster than light. Since space is stretching, I can never reach them, no matter how fast I push. They have slipped past my cosmic horizon. Those places are gone forever. So, when I ask how long it takes to cross the Milky Way, it actually feels like a small question. The Milky Way is just my local neighborhood. It is 100,000 light-years across something I can barely even imagine. It is tiny compared to the rest of the dark. But even crossing this small structure, even crossing my own galactic home, requires either 100,000 years at light speed or a long journey warped by time dilation and terrifying physical challenges. This galaxy is massive, and I feel so very small. Let's look at one more perspective together that brings this back to human terms. Imagine you are back on Earth, looking up at the night. You see our galaxy stretching across that cold darkness. That glowing band is made of billions of stars. Every single one is unreachably far from where I am sitting right now. My closest neighbor, Proxima Centauri, is 4.24 light-years away. In my current craft, it would take tens of thousands of years. At light speed, it takes over 4 years. That is just the nearest one. The far edge is 100,000 light-years away. That is 23,600 times farther than my nearest star. It is not just a longer trip. It is a totally different scale of distance. Inside my own home galaxy, there are regions so incredibly far away. They might as well be in another universe given my chances of reaching them. Yet, it is all one giant, connected machine. The Milky Way is one single galaxy. Its stars are all locked together, orbiting one center. I am just a part of it. Every star I see is part of my cosmic family. But it is a family so spread out, we will never meet. This is my paradox. It is home, but most of it is forever out of reach. I can only watch it through my senses. I can understand its bones, its history, and its makeup, but I cannot go out there and touch it directly. Not with any tech I have, or will see anytime soon. The gaps are too wide and my life is too short. I am stuck in this tiny corner, looking out and wondering, but unable to fly out and see it for myself. It is both humbling and beautiful. I live in a place so vast that light needs 100,000 years to cross. My galaxy holds between 100 billion and 400 billion stars. It has been home since the Earth was born. For as long as life has existed, humans have looked up into this void and wondered about these tiny points of light. I am here in this one spot, orbiting my specific star in this one spiral arm. But the rest of the galaxy, most of it remains out there. It is distant, mysterious, and forever beyond where my hands can reach. But it is close enough to see and study. This is the real weight behind asking how long it takes to cross. This is not just about speed, It is a question of what is possible within the hard walls of physics. It is about my place in a cosmos so big it dwarfs me. I have run the numbers. Walking would take 200 quadrillion years. Driving would take over a quadrillion years. Even the fastest craft I have built would take 150 billion trillion years. Light speed takes 100,000 years. Warped by time dilation, it might only feel like a year or two to me. But by the time I arrived, 100,000 years would have passed everywhere else. That tells me something fundamental. Crossing my galaxy is technically possible. Physics allows it, but it is beyond my reach, my tech, and my lifespan. It outlasts my entire civilization, unless something breaks or I find some new law of physics I cannot even imagine yet. For now, I am staying in my corner, and maybe that is okay. It is enough just knowing my galaxy is out there. I can study it from this distance, learn its secrets, and wonder about the other worlds hidden in the dark. I wonder about the other stars and civilizations. Maybe the journey across this place is not meant to be physical. Maybe it is a journey of understanding rather than exploration. You and I have already mapped this entire galaxy. I know its size, its shape, and its heart. I have seen how stars are born and die in its arms. I have measured its distances using the stars themselves. I have even found planets orbiting other suns from out here. I have sent my own messages out into the deep. In a sense, we have already crossed it through our shared understanding. How long to cross the Milky Way? 100,000 years at light speed, a long journey. Intellectually, you and I have already done it. The galaxy is vast, but curiosity is vaster. I have reached across those 100,000 light years with my mind and my instruments. I have crossed the Milky Way in the only way that matters, by finally understanding it, by making it part of my story, and by recognizing that I am not separate from it. I am within it, made from its matter, powered by its stars, and shaped by its history. The Milky Way is not something I cross. It is a home I live in. That is more profound than any journey. When you look up tonight at the stars, stretching across the black, remember you are looking at home. Not a destination, but home. This vast structure contains me, shapes me, and defines the cosmic context of my existence. 100,000 light years across, billions of stars, and trillions of cold, distant worlds. Somewhere in there, orbiting an ordinary yellow star, is the small rocky planet where I began, where consciousness emerged, where beings evolved to look up, measure distances, and calculate the time. To cross that expanse and understand my place in it all, looking out, that is us. That is our story. Not travelers crossing the galaxy, but part of the galaxy itself. Shaped by it, forever connected to it, even if I never physically cross the void. The Milky Way is vast beyond understanding. Crossing it takes 100,000 years at light speed. At realistic speeds, it takes much longer. It is only survivable with near light speed travel. Time dilation could help, but you would become disconnected from everything you ever knew back home. These are the facts. The physics is clear, the distances are real, the time is calculated. But there is more. You and I need to see that understanding the crossing time opens up deeper questions about what the galaxy actually is and how it was formed. What would crossing it mean? Let us step back and look at the Milky Way history. Think of it as a structure with a future. It did not always look like this. 13.66 billion years ago, after the Big Bang, the first stars began forming. These were massive stars made of hydrogen and helium, the only elements that existed then. They lived fast and died young, exploding as supernovas and scattering heavier elements into space. Those heavier elements, carbon, oxygen, and iron, became the building blocks for the next stars. They formed planets and eventually life. The Milky Way grew from a gradual accumulation of gas. Stars and dark matter gathered over billions of years. Galaxies merged, gas clouds collapsed. Stars formed in clusters and then spread out as they dissolved. This took billions of years. Even today, the Milky Way is still growing. It is still absorbing smaller galaxies wandering close. The Sagittarius dwarf galaxy is currently being torn apart and absorbed by our galaxy's gravity. Its stars are being stripped away and added to our own. In a few billion years, it vanishes. It will be fully integrated into the Milky Way. This is how galaxies grow through mergers. The view from my portal is the result of countless mergers over billions of years. Many stars in the outer halo probably came from smaller galaxies that merged long ago. When you think about crossing the Milky Way, you think about crossing billions of years of history. Every star I pass has its own story. Some are ancient, as old as the universe. Others are young, only a few million years old, still wrapped in their birth clouds. Some are solitary like my sun. Others are in systems locked in complex gravitational dances. Some are in their prime, while others are dying and swelling into massive red giants. They might collapse into white dwarfs, neutron stars, or black holes. The diversity is staggering. I would see all of it on a journey across the galaxy. Different stars and environments. You would see nurseries in the spiral arms and quiet spaces. Let us talk about those spiral arms. They are density waves where stars and gas bunch up. Think of the Perseus arm or the Scutum Centaurus arm. As the galaxy rotates, the pattern remains even as stars move in and out. Think of it like a traffic jam. Inside the arms, star formation is more active and you see young blue stars. My sun is in the Orion Spur, a safe place. Supernova explosions are rare enough that life on Earth had billions of years to evolve. If we were in a dense spiral arm, radiation from nearby explosions could strip away the Earth atmosphere. Life might never have had the chance to develop. You and I are lucky. Look, our quiet spot in the galaxy between these massive spiral arms is exactly why we're alive. If I took my ship across the Milky Way, I'd drift through those arms and the voids in between. I'd watch the view shift from glowing gas and newborn stars to these eerie, silent zones of ancient suns. The contrast is jarring, but stay with me, there's more hiding in the deep dark of this galaxy. Stars aren't everything out here. I'm seeing nebulae massive, haunting clouds of cosmic gas and dust. Some are nurseries where suns are born. I can see the Orion Nebula right now without any equipment. It looks like a blurry smudge in Orion's sword, only 1,350 light-years away. Inside that haze, hundreds of stars are igniting. Gravity is crushing gas into these tight, hot cores. Give it a few million years, and those new stars will blast the leftover gas away with pure radiation. A fresh star cluster remains, but other nebulae are just ghosts, the remains of stars reaching their violent end. A sun swells into a red giant, then vomits its layers into the void, leaving a white dwarf core. That dwarf lights up the gas, forming structures like the ring, the helix, and the cat's eye. Each one is a dead star, giving its body back to space. But supernova remnants are way more terrifying. When a giant explodes, it screams its layers into the void at insane speeds, creating the Crab Nebula. That explosion happened back in 1054. Ancient astronomers watched a terrifyingly bright new star appear in their sky. You could see it at noon for weeks. Now, a millennium later, I'm watching the debris cloud still glowing. As I drift across the Milky Way, I see endless nebulae. Some are so dim my sensors barely catch them. Others are blindingly bright, spanning dozens of light years. They remind me that this galaxy is constantly moving. It's all just one giant recycling machine. Stars ignite, they burn out, and then they melt back into space. The very atoms in my body were forged inside stars that died billions of years ago. The cycle continues. It's a chain stretching back to the start. Out here, I see this cycle playing out everywhere I look. I'm also flying past star clusters, groups of stellar siblings, all born from the same cloud of gas. Open clusters are loose families near the galactic disk. Look at the Pleiades, it's a famous cluster in Taurus. It sits 445 light-years away, with hundreds of stars that are 100 million years old. One day the cluster will drift apart and vanish, but for now, I'm watching them travel the galaxy together. Globular clusters are bigger and way older. I'm seeing massive spheres packed with millions of ancient stars. They haunt the galactic halo, way above the disk. Most are 10 to 13 billion years old. These stars are ancient and metal-poor. They lack the heavy elements I'm used to seeing in younger suns. That's because they formed early, before supernovas had time to seed the galaxy with more complex materials. Leaving the disk for the halo, I'm passing through territories ruled by these massive globular clusters. It's breathtaking. Imagine me approaching 1,000,000 stars, all jammed into a sphere just 100 light-years wide. The stellar density near the core is overwhelming. If I lived on a planet there, the night would be blinding. Darkness wouldn't exist. All those stars would make the sky brighter than any twilight I ever saw on Earth. It's gorgeous, but deadly. With stars that close, the gravitational chaos would be a nightmare for any ship. Gravity could rip planets from their orbits. Life might not stand a chance in that chaos, but who knows? I don't even know if planets can form here. These stars are so metal poor there might not be any rock. It's one of the mysteries of these ancient stellar cities. Now, I'm heading for the center of the galaxy. The galactic center is 26,000 light-years from home. I can't see it through all this thick dust, but my infrared sensors can pierce right through that dust, letting me see the madness happening down there. The center is a crowded, violent place. Stars are packed way tighter than they are back in my neighborhood. Millions of stars are crammed together here, and right at the heart lies Sagittarius A, the supermassive black hole. Sagittarius A is 4.1 million times the mass of our Sun. Thankfully, it's pretty quiet right now. It's not feeding on much today, but it's still the terrifying gravitational anchor holding this whole galaxy together. Stars are whipping around Sagittarius A at impossible speeds. I've watched S2 finish an orbit in 16 years. At its closest, it hits 3% the speed of light, only 17 light hours from that dark abyss. Up here, tracking S2 and its neighbors is how you and I confirm Sagittarius A is real. I can't actually see it. It swallows all light. I just watch stars whip around an invisible ghost. Only a supermassive black hole fits the data. On a journey across the Milky Way, passing near the galactic center would be the highlight of my mission. Provided I plot my course to keep some distance from Sagittarius A, I'd see an environment unlike anywhere else. I would see a densely packed core of stars and blistering radiation from the hot gas swirling around the void. Stars fly at relativistic speeds. It's spectacular, but deadly. I'd need heavy shielding against those extreme radiation levels. The gravity there is relentless. Passing through that region would require precise piloting and a ship built for the strain. But the payoff? Unmatched. I'd have a view of the heart of our galaxy, the anchor for billions of stars. Then there's the galactic halo. This is the massive, spherical region that wraps around the entire Milky Way disk. It's home to ancient stars and globular clusters. Most importantly, it's where the dark matter hides, reaching out far. The disk is roughly 100,000 light-years across, and only about 1,000 light-years thick. But the dark matter halo? That might stretch out 600,000 light-years or even more into the deep. Most of my galaxy's mass is tucked away in that halo, not in the visible disk I am crossing. The stars I see, the gas, and the dust, all of that is only 10 to 15% of the mass. The rest is dark matter. I don't know what it's made of. I can't see it directly, but I definitely feel its gravity pulling. Look at the outer stars. They're orbiting way faster than the visible matter should ever allow them to. The only answer is that there's a lot of extra mass out there, invisible mass, providing the intense gravity needed for those orbital speeds. That's dark matter. I'd be drifting through this halo the whole time without ever noticing it with my eyes. It doesn't play with light or ordinary matter. It only interacts with the universe through the language of gravity. It's all around me, making up most of everything out here, but I can't see it or even feel it. It's one of the great mysteries. How can most of the cosmos be invisible to us? What is it made of? Physicists have hunted these particles for decades with sensitive detectors, but so far they have found absolutely nothing. It's elusive. Now, let's consider my journey together. Not just the travel time, but what it actually means. Crossing the Milky Way means leaving everything familiar behind. Every constellation I knew is just a perspective from Earth. Move a few hundred light-years from home, and the constellations change. My familiar patterns just crumble away. New patterns emerge, travel thousands of light-years, and the sky is unrecognizable. Stars I once knew simply vanish. Faint stars become beacons. The sun, if I could still see it, would be a dim star lost among millions. Every reference point is gone. Crossing the galaxy is a journey into the unknown in the most literal sense. I can't steer by the stars because they change everywhere I go. I need high-precision instruments to survive out here. I navigate using the galactic center or known pulsars. Pulsars are spinning neutron stars that blast out radiation beams. They rotate with perfect regularity, some turning hundreds of times every second. Each pulse is timed to the microsecond. Because they're so steady, they act as cosmic lighthouses. I can triangulate my position by timing pulses from multiple stars. NASA developed technology for this, called Sextant, or Station Explorer, for X-ray timing and navigation technology. It proved that my spacecraft could determine its position in space just by detecting pulses from X-ray pulsars. This technology might be the only way I'll ever manage deep space travel or true galactic exploration. Once I'm far from Earth, landmarks don't exist. I need something universal, and pulsars fit that role perfectly. They're scattered throughout the galaxy, pulsing with clockwork precision, and I can detect them from vast distances. My ship would rely on them, but even with perfect navigation, the psychological toll would be absolutely immense. We weren't built for this. Humans evolved to live on a planet's surface under one specific star and sky. I am adapted to Earth, to its gravity, its day and night, its seasons, and its familiar, comforting patterns. Take that all away, and put me in a ship traveling through empty space for months or years. Even if time dilation helps, I'm asking a human mind to cope with an environment it wasn't prepared for. There's no natural day here. I'd have to invent cycles and spin my ship to generate fake gravity. No familiar sky outside. The isolation is crushing. Radio signals you and I send would take decades to arrive. For those on a generation ship, it isn't just a journey, it's an entire life. They're born, they live, and they die in the void. People die on this ship. For them, it is not just a vehicle. It is their whole world. The ethics are chilling. Is it fair to trap future generations out here? Kids who never chose this mission, who will never feel Earth's gravity. They are born and buried in this cold, artificial hull, all for a goal they never volunteered for. I hear some say it is no different than Earth. After all, nobody chooses where they are born. Maybe we are all on a massive ship called Earth, drifting around the sun and through the galaxy. But Earth is alive and vast. This ship, it is just a confined metal cage in the void. The morality here is heavy. If we want the stars, we have to face these dark questions. Let's look at the physics again. You and I need to explore a strange concept, the relativity of simultaneity. It is a bizarre trick of Einstein's relativity. Events that seem simultaneous to me might not be for you. Picture this. I leave Earth at near light speed, pushing toward the far edge of the Milky Way. From my seat in this cockpit, time dilates. Imagine I am moving fast enough to warp time by 10,000. While 100,000 years pass for those back home, only 10 years pass for me, a decade-long voyage. But here is the strange part. In my frame of reference inside this ship, what is happening on Earth right now is different. What someone back on Earth would claim is happening right now is totally different because of simultaneity once I am a year in. In my eyes, the date back home isn't just 10,000 years ahead. The connection is much more tangled. The whole idea of things happening at once across the void just breaks down when you are flying this fast. We would disagree on the timing of everything. Crossing the galaxy does more than separate us in space. It tears us apart in time in ways that feel impossible. There is no such thing as a universal now. Physics says there is no shared now. It is all relative. We could argue forever about which event came first. We could fight over what happened later or at the same time, as long as space keeps us apart. If we are far enough that light cannot bridge the gap, there is simply no single right answer. This is the deepest secret. Time is not a constant. It is woven into space, forming a four-dimensional fabric. My path through that fabric dictates how I age. Out here, my journey feels nothing like yours. My life would tick away so differently than anyone I left behind. Not just slower, but in a way that is fundamentally changed. You and I have to wonder how this changes our sense of identity and our place in the universe. If I ever made it back, I would return to a future Earth. Everyone I ever loved would be dust. Hundreds of thousands of years might have passed. Would I even be the same person anymore? I have only aged a few years. My memories, my soul, and my very identity feel exactly the same. But I would be a man out of time. Everything that gave my life meaning is long gone. I would be a ghost from the ancient past, kept alive by the physics of high-speed travel. Some might find that exile terrifying. Why would anyone actually do this? What is the real point? The obvious answer is exploration. I want to see what is out there and visit distant suns, searching for life, trying to understand the endless variety of worlds we have always been driven to explore. We conquered every continent and sent probes to every planet. That hunger is just part of our DNA. Stretching across the galaxy is the ultimate leap. But there might be darker, more practical reasons. Maybe we are hunting for resources. Perhaps Earth is tapped out, and we need new energy or materials. We could be running from a dying sun, a plague or war. something that makes our home a graveyard. Or we are chasing knowledge. Maybe there is something at the edge of the galaxy we have to see, an anomaly we cannot study from afar, something that demands my presence or the search for other civilizations. Our goals define the path. An exploration flight would stop at many different star systems. A refugee ship would sprint for a new home, while a contact mission follows a faint signal. Each trip brings its own dangers and risks, but all require crossing that massive, empty gap. I would have to face the limits of light and time, leaving everything familiar for the great unknown. Consider one last thing. You and I should wonder, what if humans aren't the ones making this trip? What if we sent machines? Artificial intelligence and self-replicating ships can wait through the millennia without feeling the strain. They don't need oxygen, food, or water like I do. They're perfect for the longest journeys. Sending people is dangerous, so automated probes are the most realistic way to explore. We have already started on a small scale. Voyager 1 and 2 launched back in 1977. They scanned Jupiter and Saturn, and 2 even reached Uranus and Neptune. They kept going until they punched through the edge of our solar system. Now, they're drifting in the deep dark, whispering data back. One day, their hearts will stop and they will go silent, but they will drift through the void forever unless they hit something. In 40,000 years, Voyager 1 will drift within 1.6 light-years of a star known as AC plus 79. It is not a close visit, but it is the nearest those mechanical eyes will get to another sun for a long time. If something out there is watching, something with the right tech, they might actually spot our lonely little messenger. Both probes carry golden records. They are phonograph discs filled with the sights and sounds of the world I left behind. They hold greetings in 55 languages and music from home. There are maps, too, showing exactly where Earth sits in the Milky Way. We sent them as messages to any life that might find them. The odds are nearly zero, but as an explorer, the gesture feels huge. We threw a piece of our home into the great unknown. To me, Voyager is the start of our reach into the galaxy. Soon, we could send faster ships with better sensors, maybe even self-replicating probes that could map out entire clusters of stars at once. These machines would build copies of themselves at every stop, pushing further out. It is an idea known as a von Neumann probe. Based on John von Neumann's theories, just one of these machines could eventually map every single corner of the entire Milky Way. It lands, digs for fuel, builds clones, and flings them toward the next sun. Then those copies repeat the cycle, over and over. They spread fast. Even at a fraction of light speed, one probe could eventually visit every star system in this whole galaxy. A few million years is nothing compared to the age of the stars. If someone else did this, the void should be crawling with probes. If aliens launched these billions of years ago, we should be seeing them everywhere. This is the heart of the Fermi paradox. Out here, the silence is heavy. If life is common, we should see its fingerprints across the stars, but there is nothing. Looking out my window, the galaxy looks empty. Maybe advanced life is rare, or maybe it just burns out before it can travel. Maybe they never make it to the stars, or they choose to stay hidden. Down there or up here, nobody has the answer. The silence might just be about the distance. If crossing the galaxy is as brutal as it looks, that explains the emptiness. Perhaps that is why we are alone. The vast, cold gaps between the stars might be too much for anyone to ever cross. Maybe they look at the cost of the journey and decide it is not worth it. Or maybe, just maybe, we are truly alone. What if Earth is the only spark in the dark? That would make us more precious than any star I can see from here. Crossing the galaxy would not matter much if there was no one to meet at the end. But we just do not know. The only way to be sure is to go. We have to send more probes and explorers into the deep to find the truth. So, how long would it take to cross this ocean of stars? You and I can see now that it is a complicated question. It is about more than just math. It is about the risks we take and what we are willing to lose to find answers. The physics are clear. At light speed, it takes 100,000 years. If I could fly at near light speed, time would bend. For me, the journey might only feel like a year or two. But with the engines we have now, we are talking millions of years. Those are the hard limits of our universe. These limits are set by the massive scale of the Milky Way. But the real question remains, should we even try to cross? What is the gain? What do we lose? Is the total isolation of deep space worth the price we would have to pay? Do we stay in our little corner and accept that most of the stars will always be out of reach? Each new generation will have to decide for itself as our tech gets better and our understanding of the void grows deeper. Today's impossible dream might be tomorrow's reality. But trust me, the universe does not care about our human ambitions. Space follows cold laws that do not bend for us. But within those rules, there is still room for us to explore and discover. Reaching into the cosmos is in our DNA. The Milky Way is massive, and crossing it would take countless human lifetimes. But our spirit, that spark that drives me out here, does not care about what is easy or what is simple to achieve. We measure ourselves against the edge of the possible. Crossing the galaxy is a terrifying journey, but it is not impossible, just hard. It is brutally difficult, but knowing it can be done is valuable, even if I never make the trip myself. It reminds us that the universe has rules we can understand. We can actually calculate how to cross those 100,000 light years. You and I can imagine journeys that dwarf all of history. We are part of something vast, far beyond our tiny blue world. It is about the relationship between my ambition and physical reality. These are the facts. The physics is clear. The distances are measured. But for me, the deeper truth is much simpler. We do not need to cross the Milky Way. We are already home, right here, right now, in this one miracle of a galaxy that gave us stars, planets, and life. It gave me a view of the cosmos stretching from one edge of the disk to the other. But let us push further. There is another dimension to crossing the galaxy that I must address, the practical question of survival. You and I can calculate the travel time and work out the physics of near light speed travel and time dilation. But can a crew actually survive the journey? Space is not empty. I have seen that firsthand. When we talk about the vacuum, we mean it is mostly empty, but mostly is not completely. Between the stars, there are atoms, mostly hydrogen and helium. The density is incredibly low out here. In interstellar space, I find 1 atom per cubic centimeter. On Earth, sea-level air contains 10 quintillion molecules per cubic centimeter. So space is about 10 billion times less dense than air. It is the most perfect vacuum found in nature. But when I am traveling at 99.999999% light speed, even 1 atom per cubic centimeter becomes a problem. Kinetic energy equals 1/2 times mass times velocity squared. At near light speeds, that squared term makes a massive, terrifying difference. A single hydrogen atom hitting my ship at 99.999999% light speed carries an enormous amount of energy. Each impact is like a particle in a high-energy accelerator. This happens billions of times every single second as I plow through the void. The cumulative effect is like flying through a continuous stream of radiation. My ship would heat up and the hull would erode. Without heavy shielding, I would receive a lethal dose of radiation. This is a massive engineering nightmare. I would need shields made to absorb these high-energy impacts, perhaps metal layers or magnetic fields, or perhaps a cloud of plasma pushed ahead to absorb the impacts before they reach the hull. All of these solutions add mass and complexity. They make my journey harder, not easier. And then there is the dust. Space is actually quite filthy. There are grains of carbon and silicon. They are microscopic, but at light speed, they hit like bombs. A tiny grain traveling at near light speed hits with energy equivalent to several kilograms of TNT. Space contains billions of them per cubic kilometer. On my journey across the galaxy, I would hit countless grains. Each one is a potential catastrophe if it breaches my shielding. Avoiding them is physically impossible for me. I cannot steer around them. I have to go through. My shields must be able to handle constant fire. These impacts range from atoms to dust. My ship must endure this for years of my own time. The engineering challenges are staggering, but let us assume they are solvable through some future advanced technology. Let us assume we find those systems. But you and I still face another problem: acceleration and slowing down. To reach high speed, I have to accelerate and eventually decelerate. Both processes take time and power. How much force can my body tolerate? Humans handle 3 or 4 Gs for extended periods. Fighter pilots experience 9 Gs briefly, but for me, sustained high acceleration is a death sentence. It crushes my circulatory system and starves my brain of blood. It causes blackouts, or even worse. Let us say I limit my acceleration to 1 G. That feels just like standing on Earth. I could live at 1 G indefinitely. At 1 G, how long until I hit near light speed? The speed of light is 980 million meters per second. 1 g is 9.8. Divide speed by acceleration and you get a time of about 1 year. 1 year of constant pushing at 1 g reaches light speed. I cannot actually reach light speed because of relativity, but I can get close. Say I accelerate at 1 g for a year. Now I am cruising at 99% of light speed. My ship is finally across the void. Eventually I must decelerate for another year at 1 g. Total time for me is about 2 years plus the cruise. That sounds manageable, but you and I have a problem. Accelerating at 1 g for a year requires energy a truly staggering amount. Suppose my spacecraft has a mass of 1,000 tons or 1 million kilograms. That is small, but let us use it as a baseline. My kinetic energy at 99% light speed is roughly 7 times my rest mass energy. Rest mass energy equals mass times light speed squared. For 1 million kilograms, that is 900 sextillion joules. At 99% light speed, that energy is 6,000 sextillion joules. That is the energy I need to input. If I use a rocket, I carry fuel, but fuel has mass. This creates the rocket equation trap. My biggest hurdle out here is mass. More fuel means more weight, requiring even more fuel just to move. It is a vicious cycle that chemical rockets simply cannot break. Nuclear engines might nudge me a bit further, but matter-antimatter annihilation is the holy grail. It converts mass directly into raw energy with perfect efficiency. Even then, the logistics are terrifying. I would need a fuel load as heavy as my entire ship. Plus, I have to carry enough to slow down at the end. Maybe I do not carry the power at all. A massive laser from home could theoretically push against a light sail attached to my hull. If that beam stays locked on, I keep speeding up. 0 fuel required on board. But light bleeds over distance. A laser spreads out as it travels through the void. To reach another star, that beam would need a focus that defies imagination. And that only gets me moving. To stop, I would need another laser waiting for me at the destination. That means someone has to be there first. The physics are brutal. Hitting near light speed demands an energy input that is frankly staggering. There is no cheating the math. That energy has to come from somewhere in the dark. I either carry the weight or rely on massive infrastructure I can barely fathom. Stick with me, let us consider a different path together. What if I did not do it in one go? Imagine taking short hops from Earth to the nearest star, only 4 light years away. Then I push on to the next one, maybe 5 light years further, just hopping from sun to sun across the Milky Way. The steps are smaller, sure, but there are so many. Our galaxy spans about 100,000 light years of empty space. At 5 light years per jump, I would need 20,000 stops to cross this galaxy. Every single time, I have to slow down. I would rest in a new system, then burn toward the next. If each leg takes 10 years of my life on this ship, between the burns and exploring, those 20,000 jumps would take 200,000 years. I am right back to a generation ship scenario. Jumping does not save time for a full crossing, only for local scouting. We need to look closer at how I would actually navigate this void. Out here, space is 3-dimensional. The galaxy is not flat. It is a disk, 1,000 light-years thick, with stars packed into a central layer. That core layer is 300 light-years deep, surrounded by stars above and below. The galactic halo stretches thousands of light-years further out. Crossing this means choosing a 3-dimensional path. Do I stick to the crowded plane where the star systems are thickest? Or do I bank high above the plane to avoid the traffic? Every choice changes the mission. The plane offers more planets and wonders, but it is also full of hazards like dense dust clouds. Up here, above the disk, the navigation is easier and the space is clear. Of course, there are fewer landmarks and less to see. My survival depends on my goals. Every detour eats into my time. A straight line is the shortest route, but out here, a straight line might lead me right into a cosmic nightmare. Sometimes taking the long way around a hazard is actually safer. But you and I have to ask, how do I stay on track? A tiny error out here becomes a catastrophe. If my heading is off by 1 degree, I will miss my target by thousands of light years. I would need constant adjustments. That means burning fuel to slow down, turn, and then accelerate all over again. Every tweak costs me time and power. I have to rely on my instruments to make micro-adjustments to my path constantly. But tech fails. Sensors drift after decades in the deep cold. My equipment is slowly degrading out here in the radiation. Redundancy is my only hope. I need backups for my backups. This ship requires a level of reliability we have not even invented yet. Then there is me, the human factor. Keeping a biological organism alive in this void is far harder than maintaining any machine. I need air, food, and water. Every recycling system on this vessel has to work perfectly for my entire life. A closed-loop life support system must run for years without any outside help. We have tried building these on Earth, but it is hard. Biosphere 2 was our big test at home. It failed. Oxygen plummeted, and carbon dioxide turned the air into a toxic trap. They could not grow enough food. It proved that balancing an ecosystem is nearly impossible, even with Earth resources right outside the glass. Out here, I have to be perfect. One small break in my ecological chain, and I am either starving or suffocating in the dark. There are no supply runs, no help is coming. Out here, I am truly alone. That is why we talk about suspended animation. It might be the only way to survive these long years between the stars. If I can just shut down my metabolism, I will not need air or food. The ship just keeps me on life support. Just freeze me and wake me up at the end. But we do not have that yet. We can freeze cells, but humans? No. Reviving a person without damage is science fiction. Ice crystals would form in my blood and rip my cell membranes apart. Anti-freeze chemicals could stop the ice, but at the levels I would need, they would just poison me from the inside out. Some creatures do it naturally. Wood frogs can freeze solid in the winter and just hop away when the spring thaw comes. Their bodies produce natural compounds that shield their cells from the jagged edges of ice crystals. If I could replicate that trick, maybe I would survive. But for now, you and I are still staring into the unknown. For my crew and me to survive out here, we need a life support system that never fails. I either need my team awake and alert, or we have to turn this ship into a floating village. On a ship like this, generations live and die in transit. The social challenges are absolutely immense. How do I maintain order? What structure works? How do we resolve conflict when no one can leave? Keeping morale high when the journey outlasts your own life is a question with no easy answer. History tells me isolated groups change in ways we cannot predict. Some thrive, but many others collapse. Up here, there is no backup plan. If our society fails, we all die. Social design is everything. I would have to design the education and traditions that hold our small community together. It is engineering a civilization on a massive scale. Now, let me show you what I see. We have talked about the physics and the fuel. What about the experience of crossing the galaxy? Looking out my viewport, the galaxy appears as a thick, glowing band across the dark sky. I am staring through the edge toward the galactic center, where the light is brighter and denser. Turn the ship toward the outer edge, and it dims. My view changes every second I move. If I climb above the galactic plane, that flat band slowly opens into a massive disc shape. I see the spiral arms clearly now. The whole structure looks like a pinwheel. It is breathtaking. Billions of stars are spread out in these perfect patterns, but I am leaving it behind. The sky turns pitch black as I drift further away. Eventually, I enter the intergalactic void, seeing the Milky Way as just a small, distant spiral. It is beautiful, yet distant. Within the disk itself, however, the transformation is much slower. Stars drift past. Some flare bright as I approach, then fade away as I move past. Familiar patterns dissolve. Near the center of the galaxy, the sky is so crowded it glows. There are so many suns that they bleed together. The night sky is never truly dark. Out on the rim, the stars are few and far between. It is a lonelier view. I pass through nebulae so vast they span hundreds of light years across the deep void. I see glowing clouds in reds and blues, the signature colors of hydrogen and oxygen gas. Dark dust clouds look like black patches spilled against the background of stars. I see regions of starbirth and the violent debris of massive supernova deaths. This galaxy is not uniform. I see every part of this patchwork on my long journey. Then there is time. If I push my ship fast enough, this crossing might only take months. But for you back on Earth, millennia have passed. It is a strange, unsettling disconnect. I watch a star drift by. Behind that single point of light, decades of history have vanished. By the time I pass a single star, generations have been born and died back home. Entire empires have fallen. The entire course of human history could play out in the time I cross one small section. It is disorienting. I am moving through space while watching the entire universe grow old. That is the price of speed. I reach the stars, but I lose my world forever. Now, consider what happens when I arrive. Suppose I successfully cross the Milky Way, traveling 100,000 light years. I reach the far edge. If I were just a probe, I would start observations. I would study these alien stars and beam data home, knowing it takes 1,000 centuries to arrive. As a pilot on a crewed mission, I would look for a world to call home. But 100,000 years have passed back home. Any message I send is already ancient history. Everyone who sent me is gone. Their entire civilization might be gone too. Humanity might have changed beyond all recognition. I am effectively and completely alone out here. I can never go home. Home is a ghost. I am just a relic from the past. My only choice is to build a new home or head toward another distant galaxy. The Milky Way is tiny compared to deep space. Andromeda is 2.5 million light-years away. To reach it, you and I would need 2.5 million years. Even those satellite clouds, the small galaxies orbiting us, are 160,000 light-years out. Reaching another galaxy? That's a journey on a terrifying scale. This galaxy is our neighborhood, yet crossing it is hard enough. Reaching another one feels almost impossible. In a way, this edge is our ultimate limit. Beyond it, space becomes a wall we can't climb without rewriting the laws of physics. Unless we stumble upon a secret of the universe we haven't unlocked yet. Warp drives or wormholes might change things, but for now, this vast arena is the only stage where our future will ever play out. It is home. Even if we leave Earth and drift among the stars, these galactic walls remain our final boundary. 100,000 light-years across. That is the size of the cage we live in, holding billions of burning stars. Light needs 100,000 years just to cross it. It's too big for our minds, yet we try to measure it. We've mapped its shape and studied its bones. We know its past and its dark future, and exactly where we drift inside. I've looked out and seen what we've mapped: millions of stars, the glowing center, and those long, ghostly spiral arms. We know planets are everywhere out here, but we've listened for voices in the dark and heard only silence. Still, we listen. This expanse is ours to study, and maybe one day we will truly sail it. But traversing that width? It's the greatest challenge I can imagine. The math says yes, but our hands can't reach that far. Perhaps there's a reason for this distance. Maybe the scale is meant to give us room to grow before we ever meet. Isolation stops us from colliding too soon. And in that lonely silence, something unique begins to grow. If others are out here, they're so far away they must evolve alone. Each world follows its own path, building a culture we've never dreamed of. If we ever bridge that gap, you and I will find something completely alien waiting for us. Not just neighbors, but an entirely different story of life. That's a mystery worth keeping. The isolation is worth it. This massive scale is what makes true diversity possible. That variety of life, wandering down independent paths, is the most precious thing in the void. Asking how long it takes to cross this place isn't about speed. It's about the nature of our home. It's about the cold gaps between stars and the lonely silence imposed by a galaxy this big. What would it take to break that silence? The answer isn't as simple as you'd think. At light speed, it takes 100,000 years. But with time dilation, an astronaut might actually survive that crossing. But you'd lose your home forever. It takes tech we don't have and courage we haven't tested. This place is huge. Crossing this void is the final test. It will take every bit of our science and every ounce of human will. Even if we succeed and cross those 100,000 light years, we'll arrive as strangers, separated from our former lives by eons. That is the cold reality. But the deeper question isn't whether we can make the jump, it's whether we should. Every generation must decide for itself, right here in this incredible galaxy that gave us life and a place to stand. We have a view that stretches from edge to edge. But this journey isn't measured in miles. It's measured in what we learn, and together, we've already taken the first steps. Thanks for being here tonight. If this journey meant something to you, please like the video and subscribe to the channel. Your support keeps me out here, exploring the dark. Next time you see those stars, remember that is home. A place so massive that light takes eons to cross it. We might never truly walk its width, yet it's familiar. We've mapped it and made it part of our soul. We are tiny, but we are here. It's extraordinary. Good night, and sleep well under the stars of our beautiful eternal home.